pseudo-Boson language. That is, you see that this mass goes to 0 if you take it to C to infinity, or if you take top Quark mass to 0. The reason is that in this limit, sin gamma goes to 0. You can go back to like this. You basically take sin gamma to 0. Basically, top Quark mass goes to 0. Now, when you go back here, if sin gamma goes to 0, that means this tapo term is 0. This tapo term is 0. This is already 0 by rotation. So basically, if in that case, there's no explicit breaking of U3 symmetry at all. So the U3 symmetry breaking comes from this tapo term, basically coming from the underlying vector-like fermion mass. This is, in some sense, a bit like QCD dynamics, where the pion mass comes from the up and down Quark mass you write down, which are small explicit symmetry breaking effect. So that's why the Higgs mass is also gets suppressed in this way. Now, for this ratio, we can, since the theory is strongly coupled, we cannot calculate exactly, but we can estimate how big it is. Now, earlier we said that in the fermion loop approximation, it is 1. However, at the lower energy, this ratio changes through the RG equation. And if you run it for a long time, there's a quasi-IR fixed point about 0.4. If we don't assume a large separation between composite scale and the scalar symmetry breaking scale, we cannot really use the RG because there's not large suppression. We cannot really believe that it runs through a long time and go to this. But if we assume the thing is continuous, then we would expect that this ratio should lie somehow in between these two numbers. So, but even if we take it to be maximum, let's put an upper bound of Higgs boson mass to be about 185 GeV.
Okay, let's say why is it greater than 0.4? So shouldn't you get a lower bound?
No, there's no lower bound because we still have this factor, which is smaller than 1.
The charge mass is large. Are you saying this thing can also be a suppression factor?
Yeah, that's a suppression factor. In fact, there will be a lower bound later, just because we have to assume this. Even if you assume the coding coupling is 0 at the high scale, it will run to some positive number at the low scale. So there will be a lower bound. Basically, even if this is our tree-level result, right? If you want to really calculate the Higgs boson mass, you still need to run this coupling down to the Higgs boson mass in order to calculate. Just by running, even if you take it to be 0, it will become positive at the low scale. Now, this is just saying, well, if it, of course, charge Higgs mass is not 0, but this can also be very big. So this can be dependent on what. Now, in fact, this is not the only explicit U3 breaking effect. We also know because there are also electroweak interaction, which certainly distinguish doublet from singular. Now, this effect is just like the mass difference between the charged pion and the neutral pion, which receive this electromagnetic loop correction. And usually, in that case, we can calculate the quadratic divergent contribution between the charged pion and neutral pion is cut off by roughly rho max. So here, similarly, this interaction also is quadratic divergent contribution, so we also need to cut it off. By analogy, we take the cutoff parameterized by some capital M rho, which is presumably related to some vector particle of underlying theory. One finds that both corrections, well, all these radiated corrections reduce the Higgs boson mass, and the effect can be significant. If M rho is too big, cutoff is too big, one can even turn the Higgs boson mass negative. Therefore, we are sitting in the wrong vector. So there's also limited on this cutoff of the electric gauge loop. But the good thing is that things always reduce the Higgs boson mass. So our upper bound still applies. Basically, the Higgs boson is because you throw this thing can become arbitrarily heavy again. This means this model, the Higgs boson is really light in this case. Has to be light. So these are some analytical estimates. We can try to verify it through some numerical calculation. One can first we enumerate the input parameters. After we fix the electric symmetry breaking scale and the top Quark mass, then there are 6 independent parameters. 3-dimensionless one and 3-dimensional one. There are this Yukawa coupling, the 2 quartic coupling, and the chiral symmetry breaking scale, which is related to the charge Higgs boson mass, and the cutoff for the electroweak gauge loop. Now it's more convenient to take the ratio of these, either the couplings or the mass scale ratios as the input parameter, because they are better constrained. And also the formula also depends on these ratios. So we can look at the expected range of these numbers. First, the Yukawa coupling we expect to be 3 to 4, as we earlier discussed in NGL type model. This is the range. Now this ratio is between we estimate to be between 0.4 and 1. This is the fermion loop approximation. Now this is the quasi-infrared fixed point. Now here is some, for example, one loop RG equation. You assume some initial point ratio, then you run it down. You find take different initial value, it quickly run towards this quasi-infrared fixed point. Even though you cannot really trust this one loop RG near this region, you at least if you run it for a long time, you don't expect to go below this number. So you expect it to lie between 1 and 0.4. Now this ratio also has a quasi-infrared fixed point of -0.2. And initially, since there's no fermion loop contribution to lambda 2, you start with 0. So you expect this range. Now, for the mass scales, you have the constraint on the chiral symmetry breaking scale. The biggest constraint is coming from the T parameter, basically the Weak-isospin violation. Turns out to be very strong. It will require the chiral symmetry breaking scale to be bigger than 3.5 TeV. We will discuss this more later. Then the charge Higgs boson and the rho we just assume to be within below the cutoff, which is taken to be 4 pi n.
So lambda 1 is very, very strong.
Yes.
So did you, but you're still doing things, as you said, somewhat at tree level, right? So the Higgs potential is such a strong lambda 1.
Yeah, but the Higgs potential really just depends on this ratio, which is pretty stable.
It's actually stable, but I thought lambda 1 is some form of the IT5 kind mixing.
Lambda 1 is this is the quartic coupling, basically the quartic coupling of NGL. And let's see, the mass term doesn't really depend on lambda 1 too much. As long as lambda 1 is big, basically don't really affect this part. Otherwise, it's controlled by the ratio. Now it turns out, in fact, the Higgs boson mass mostly just depends on these 3 parameters. They are very insensitive to these 3. The Yukawa coupling itself, lambda 2 is small anyway, and also the chiral symmetry breaking scale. One can basically see this is true numerically. Also, one can see that the approximate formula basically depends on these 3 ratios. This is due to the negative contribution of the electroweak loop. These are coming from the tree level approximate formula. And then one can just choose some typical value for this and vary these three numbers. So we draw two parameters, these two on the axis, and choose a few of the different M rows. And one finds that this is the prediction of Higgs boson mass. For M row equal to 0, that means you assume there's no electroweak gauge loop corrections. So if you just take some typical value, you see this 106 GeV lies here. And 106 GeV can easily lies within the allowed parameter space. And the upper bound is roughly 175 GeV, which is consistent with our approximate formula. Right? It's a bit lower because we really push it to the limit. And there's also a lower bound. You can see about 80 GeV. This comes from the fact that even if you take the quantum coupling to be 0 at about 10 TeV scale, when you round it down, the Higgs boson gets a mass about 80 GeV. Just a little bit possible. So one can say that such a model would prefer the Higgs boson to be within this range, 80 to 170 GeV. Certainly 106 GeV is very consistent with this range, even though we cannot make very precise prediction. Okay, earlier we said that the main constraint of this model coming from the weak-isospin T Parameter from the T prime loop. The reason is because the U3 global symmetry does not contain a custodial SU2 symmetry. Therefore, you do have large custodial SU2 symmetry breaking effect. The biggest effect is coming from the heavy T prime, the heavy top partner loop. And one can calculate with this formula, and one finds that also earlier you say the bottom effect also give a contribution, which is a bit smaller than this one. One finds that if you require T to be less than 0.1, then you need F to be bigger than about 4.3 TeV. This is 68% confidence. So roughly F has to be bigger than 4 TeV. Which means that it does require some tuning in this model, because the tuning of this model is basically measured by V squared over F squared, where V is 250 GeV. If F has to be 4 TeV, now the tuning is worse than 1%.
You mean tuning to make the potential?
Yeah, basically tuning among different parameters in the Higgs potential to make V much smaller than F.
That's a general problem of all of this model.
Yes, yes, it is true. Now, for other states, we can just count how many other states. The long effective theory contains 2 doublets and 2 scalar singlets. So that means other than the Higgs boson, the light Higgs boson, we still have 3 CP even and 3 CP odd, the neutral scalars, and 1 charge scalar here. The mass of the charge scalar was used in the input parameter, but we can see that if one have a Higgs boson mass of 126 GeV, this will put a constraint on the rho and the charge Higgs mass. The charge Higgs mass has to be at least bigger than twice of F. F is already 8 GeV, so that means charge Higgs mass has to be above, at least roughly 10 GeV or even above. Most of our other states are quite heavy. There's one relatively light state because we have U3 breaking down to U2, which has 5 Goldstone boson. So there's one additional Goldstone boson, which is a CPR, the neutral scalar, but it's mostly a singlet. The mass is related to the Higgs boson mass in this way, F over V times the Higgs boson mass. So it's also much heavier than the Higgs boson mass. Roughly it's 1.5 TeV-ish if you get in this model. Unfortunately, because it's mostly a singlet, the cross section too small. Even for high luminosity LHC, this 1.5 TeV is out of reach of such a high luminosity LHC. Now, other scalars are above 10 TeV, so there's no hope for LHC. Now, how about the Higgs coupling? Again, because once you do this tuning, you push F higher, this model is close to the decoupling limit. Now, all the corrections goes like V squared over F squared. So the Higgs coupling correction is also like V squared over F squared is less than 0.2%. So this is also cannot be tested at LHC. At the future lepton collider, this is also quite difficult. And T prime mass is roughly 10 TeV-ish, which may be reachable by 100 TeV collider. So, okay. So this is the minimal model. Well, the good thing is that it can explain the Higgs boson mass and also right now consistent with all the experimental constraints. But the one can say the bad thing is the prediction is that all heavy states are out of reach of immediate future colliders, so it's hard to test this model immediately. Also, it requires severe fine-tuning in this model. The reason is due to this weak-isospin breaking. So one can imagine that whether one can extend this model to include the SU2 custodial symmetry, so that one can lower the chiral symmetry breaking scale, and therefore reduce fine-tuning. Also, all other states can be lighter. Maybe there's some chance to be tested at the near future colliders. So this is the first thing one can immediately think is to include the bottom, right? You include the right-hand bottom, you can do the custodial SU2 symmetric model, and then you extend the model through a bottom seesaw sector. One can do that. However, doing this also introduces a new problem. That is, now your left-handed bottom quark mixed with a singlet. Let's change the bottom quark coupling to the Z. Now there's a very strong constraint from the Z to BB bar. Now right now, the experimental value is already like more than 2 sigma away from the standard model prediction. Now if you have this effect, it might make it worse. It goes in the wrong direction. So one doesn't want to do that. One can just play these two things, choose the appropriate parameter. One may try to satisfy both the T parameter and Z to BB bar. One can slightly reduce the F, maybe from 3.5 to 2.5 TeV. And the T prime is up to maybe 3.5 TeV, but it's still quite heavy. If one really want to lower, to minimize the tuning, to lower the T prime mass, one really one need to do a different assignment, a different extension. Now this was discussed by Agashi et al. When they built this composite model. They also noticed the same problem. So they found a very smart way to avoid both problems. That is, they don't assign the TB left-handed as a 2-1 under the SU2 left cross SU2 right. Instead, they assign this as a 2-2 under SU2 left cross SU2 right to preserve the custodial SU2 symmetry. Of course, to do that, one has to introduce another doublet which pair with this doublet to form a 2-2 representation under this SU2 cross SU2. Now, doing this with additional left and right parity symmetry, you can protect the Z to BB bound. Okay.
This one has some observable consequence, I think, with the 3 Higgs versus 2 Higgs production, right? I mean, triple Higgs.
Usually, the immediate the most distinctive thing is this charge 5/3 top pattern. This guy.
I think this symmetry also sets a selection rule forbidding 3 Higgs triple Higgs production. So there are, I think there are some ideas on how to even check this in the future.
Yeah, triple Higgs coupling is always it's difficult, right?
Yeah. Yeah, it goes very far in time.
Experimentally also very hard. So basically you need an additional vector like a doublet, but with hypercharge is 7.6. So in fact, in terms of electric charge, this is 5/3, this is 2/3. So this has the same charge as the top. Therefore, we denote it as capital T. But this one is the exotic one. Now, the point is not. Let me just say the idea is that you introduce this guy. Of course, you have to explicitly. We haven't seen these guys, so they must be massive. Now, if they are, you take their mass to infinity, you recover our minimal model. Then it doesn't help with the Custodial symmetry, right? So they must be light enough to help with the T problem. But if they are too light, they are basically, if they are degenerate with this guy, then the whole thing is SU2 plus SU2 symmetric. Basically, this will remove the T parameter contribution from the standard model top bottom. Therefore, if these are very light, then in fact you get a negative T parameter because you remove the standard model contribution. So this means that in some range in between, not very light, not in infinite mass, there must, just by continuity, there's a range where the T parameter can be right, can be close to 0 and consistent with the model. So this is the idea. So in fact, this will have some prediction on the mass of these guys. Now the dynamics is something I may not want to go through detail. Basically, you introduce two more. Basically, a pair of vector-like quarks, so the symmetry becomes bigger. You start with U5 cross U4 symmetry. The U5 is between these five guys. You still need this additional singular chiral fermions. Of course, you don't really need such a big symmetry. What you really need is O4 subgroup of the U5 to preserve this custodial SU2 symmetry. You just need an O4 spontaneously broken down to O5 spontaneously broken down to O4, then you will have this custodial SU2 symmetry to protect the T parameter. So we will do that by explicit breaking term to reduce that. That's what we will do. So let's start with the strong dynamics, which is preserving this. So you can form these are 20 scalar states. We get a label by this way. And the light guy coming, the one which break chiral symmetry is this one. We assume these three are heavy, so we will integrate them out. And the explicit breaking of the O5 symmetry coming from this fermion mass term. We have now three of them. These two we have seen before. We introduced this vector-like doublet. They can also have an explicit mass term. Now, therefore, this mass term turns into tapo term in the scalar potential, like this. This is scalar potential. Now, to a first approximation, if you assume these other scalars are heavy, you integrate them out. The only effect is coming from their wave. Their wave are induced by this tapo term. But even if they are heavy, they still can have some wave like this. This is the doublet. This is the wave coming from the state of this exotic quark, and this is the what we discussed before. Now, these are the explicit breaking terms. Now, in this model, so far we still have a U5 symmetry which can produce two light Higgs doublets. One made of the usual T top bottom, the other made of this exotic new quark. We don't want two light Higgs doublets, so in fact we write down an explicit breaking term to break a U5 down to O5 to remove one linear combination, basically to make one linear combination heavy. is basically that's what it does. So now, once we include this term, the symmetry is broken down to O5. And O5 is spontaneously broken by the negative mass square, and down to O4, and produce 4 boson, which are identified as the Higgs field. Again, we can minimize the potential. You find that is phi t, these two light neutral components get wrapped like this. These are electroweak symmetry breaking waves, so their sum need to be 246 GeV. The 10 beta, the ratio has to be close to 1 to preserve custodial SU2 symmetry. Right? It's a bit larger than 1 because we still need a little bit custodial breaking effect to account for the top-bottom contribution.
How much is the top-bottom splitting?
Top-bottom split.
And mass split? I
mean,
that contributes from the T, right? Also.
Right. Top is just 173, bottom is about 5 G. Right? That gives you a contribution to the.
I thought you were talking about.
To the one. But because we introduced the new XT, if they are light, they cancel the contribution from the top-bottom loop because they make the whole thing custodial SU2 symmetric. So we don't want to completely remove that contribution. We still need a little bit left, right? That's basically the idea. So the generalized, now we have one additional top quark. So the top seesaw mechanism is generalized to a 3x3 mass matrix, but we can do the similar way. We find the top quark mass is given by this, suppressed by this factor. Because C is big, but you just choose this ratio to compensate that, but you can get the top quark mass to be correct. This requires UT over F to be this ratio. Remember, F is the parasymmetry breaking scale. UT is the explicit breaking. Now the two heavy top partners, one is the mass roughly given by this is the X, this exotic quark mass. The other is just the top partner times the parasymmetry breaking scale. It's usually about 2 to 3 times F. Turns out we will see later this mass needs to be less than F. So this will be the first state to be seen in this model. Now currently we already have a strong bond from CMS on this exotic quark to be heavier than 800 GeV. Now earlier we already discussed that in the limit when mx goes to 0, then adding this cancels the standard model contribution. Therefore, the T would be negative. On the other limit, when mu2 goes to infinity, this decouples. We go back to the minimal model. The T parameter contribution is very large. So there should be some within suitable mass scale. You should find a T value which is compatible with the precision measurement data. Okay, one can also do calculate the Higgs boson mass. This is the mass matrix. One can just diagonalize that. One finds that this is the Higgs boson formula. The first part is similar to the previous one. There's a negative contribution due to this doublet mass. Okay, both these effects are explicit breaking. So you see that if these two are 0, your Higgs becomes the exact Boson boson. Also, electrically engaged loop will also reduce the Higgs boson mass. Now, numerical turns out with some very typical parameters, one can find the Higgs mass right within the correct mass region, and these are the mass of the charge factors quark mass. This is 10 beta, which control the T parameter. This is a